Hey guys, this is Jillian. Today I'm going to be teaching you about implicit differentiation. Basically, implicit differentiation is when we cannot isolate a variable in order to compute it for a derivative. For example, in order to make this make more sense, in the equation y squared minus y plus 1 is equal to x cubed minus 2x squared plus 4x minus 3, y cannot be isolated by itself, and therefore we cannot use the normal way we use to find the derivative, or y prime, or dy d of x, depending on what you want to call it. Therefore, we must use implicit differentiation in order to find y prime. However, in order to find y prime, every time we find the derivative of y, like how we would normally take a derivative of a variable, for example, how we normally take x squared is normally just 2 of x. For example, y squared would be 2y. But because we want to find the derivative of y prime, we must also multiply the the variable we computed, 2y, with dy d of x, or x in terms of the derivative y. Therefore, we can later find the y prime, because we then isolate dy d of x and find that y prime. And we only use implicit differentiation when the value we are computing the derivative of cannot be isolated. Like in the example we just discussed, the y could not be isolated within that example. We're going to go over a few example problems. However, I'm probably not going to go into as much detail as I normally do with problems, because for sake of time, really. Basically, in the first problem, we use sine and cosine trig identities and trig derivative identity formulas in order to properly compute the y prime. Again, you must not forget dy d of x when finding the derivative of y. Every time you find the derivative of y, you must also multiply by dy d of x. This will allow you to find the prime, y prime, or derivative of y. Again, in the next problem, you will see, upon close inspection, the dy d of x. It's a slightly more complicated problem with product rule, with some trig identities as well in there. But basically, we want to isolate that dy d of x in the end. It becomes a kind of long problem, long answer, but we do want to find the dy d of x, and most of the time, once you get that general formula, once you apply that general formula, the product rule, the chain rule, using that dy d of x, everything else is just algebra and trying to figure out the rest of that equation there. So we have a few more problems. There's a total of 10 tonight that we will go through, all of different variations in of strength and variations of type, but they're all examples of implicit differentiation. For example, this one, chain rule again, but this is only using y's and x's. There's no trig identities in here at all. So basically, again, we just isolate that dy d of x. In this case, it was pretty easy to isolate. We didn't have to subtract anything over. We just kind of find derivatives of both sides and then divide it over, so that way dy d of x is by itself. I can't stress how important enough, but people do forget to add dy d of x when they're finding that y derivative on that one side. But you must always multiply dy d of x when to that y derivative. For example, in this one, we have the 4y cubed is an example of a derivative of the y to the fourth minus 2. 4y cubed is that derivative, and we must therefore also multiply it by dy d of x. Again, we isolate dy d of x. This one kind of includes a quotient rule, so it's a little bit more trickier, a little bit more tedious, but we are able to isolate that dy d of x in the end. Some things cancel out, actually, in this equation, which it makes it actually kind of more simplified if you think about it, but it did work out in the end. We also have this one, 5 tangent of x, 5, which is x cubed of tangent secant squared of 3 of y. This one, again, has some chain rules in there, and we kind of have to multiply by the original function, then by the derivative, and derivative of the inside function, and so on and so forth. Basically, for that, we just, again, use the proper derivative, but because this is not multiple different equations or multiple different numbers being multiplied or finding the derivative, it's just one number being trying to find that derivative going all the way down, breaking it all the way down. We don't multiply it by multiple d of x's. dy of d of x is. We only multiply it by 1 dy d of x. In the end, it's pretty easy to simplify, divide it back over, and it's isolate that dy d of x. Again, dy d of x, cannot stress how important it is to put that there. Also, next question, we have, again, a quotient rule there, and we want to try and isolate that dy d of x. It gets some pretty large numbers later on in there, but it's pretty simple, pretty straightforward, kind of simplifies out pretty nicely. We isolate that dy d of x. We get that quotient rule going, we simplify, factor things out. A lot of it is just algebra based once you already apply the knowledge of derivatives. Again, sine of x squared y squared is equal to x. Kind of find dy d of x on that one side. And as soon as you do that, you're able to finally compute and find dy d of x. Again, 8, you're finding dy d of x. It's very simple, pretty straightforward at this point. You want to find that dy d of x. You cannot forget that dy d of x. It gets a little more complicated in number 8 with the e squared or e to the x, and then you're finding derivative and all that stuff. For e to the x power, you don't need that dy d of x. You only need it for when you're multiplying by y values. In that case, it's only on the right side of this equation. And because it's only on the right side of the equation, we only use it once. It seems like it's kind of stuck in there randomly, but once you figure it out, once you kind of multiply things out, divide things out, you're able to isolate that dy d of x fairly easily. All right, second to last question, we have our some more trig with chain rules there. And the dy d of x, again, is being used to find that y prime, that y derivative of y, dy d of x. You isolate dy d of x, cannot forget that dy d of x is actually pretty simple out, divided to the other side. Nice and simple for you. 10, we have a squared square root of a number of a function y to the 4th, so we must also add that dy d of x in there as well in order to later isolate dy d of x in order to find that dy d of x, y prime derivative of y for that function. Again, these are all examples of implicit differentiation. I didn't go into huge detail about each of the problems and how I was able to answer each of those problems because they're kind of long problems. However, I did kind of go over the general basics and the general trends that do show up with these implicit differentiation problems, and that is you must always include dy d of x. If you do not, it becomes an issue. But that's all for tonight, and thank you so much for watching.